right, so let's go ahead and get into our derivation of basically the Young's modulus, or our stiffness of our material, based on kind of the atomistic basis of linear elasticity. So we want to calculate the stiffness. So we could actually simplify our expression quite a bit. So instead of looking at the internal energy per bond or per atom, we could start actually, one of the ways we can kind of derive this expression is by looking at the atomic volume, or this kind of omega. So if I look over here, instead of looking at the volume, I could just look at the atomic volume, so omega. So I still have my expression here. Where did my entropy term go? Well, we're looking at metals to begin with, so we don't care about that. So I also know that in my, I have the following expression, that in my elastic regime, I'm linear. This is my function for stress and strain. So I could rewrite my Young's modulus as the slope. So the change, d sigma, d strain. So that then propagates, and so I could see here, I get this expression now for my Young's modulus. So my Young's modulus is proportional to the curvature, the second derivative of my potential. So, and then again, there's this constant of the atomic volume. We're not going to care too much about this, and actually you'll see that unless you use very, 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 very accurate potentials, your Young's modulus is going to be quite a bit off. But the key thing here is my Young's modulus is proportional to the curvature of my potential. And we've talked about, and you'll see in the problem sets, that there's quite a few potentials that you'll run into. So typically, again, the first term, if there's a negative term, there's an attractive term, and then there's a repulsive term. So they usually take kind of the following form. So M is typically 1 for ionic crystals, covalent metallic bonding. Actually, 1 for ionic crystals. For covalent metallic bonding, it could be 4 to 6. A repulsive term, B, can be constant. Again, the N exponent can be 9 to 12 for different materials. But we can start now, again, so we have our expression that again, it's proportional, actually, excuse me, I jumped ahead actually. It's proportional to the curvature, not of our potential curve, but we're going to work towards that. So, shoot, I gave away the game. But anyways, so Young's modulus is proportional to U over my strain. But, again, if I look at my general potential, ULJ, right here is a function of R, I could rewrite strain, because right now I have this expression. So it's 1 over omega d squared u d epsilon squared. And I know that this is just basically the distance between my atoms. So right here, there's basically that distance, the equilibrium distance, and then we're separating them larger. So if I'm stretching my material, I could relate, essentially, this r distance to my strain. And actually, we could write it here. The strain, if I'm looking at, especially if I'm looking at a 1D system, my strain is just going to be the current position, r, of my, or the interatomic distance of my atoms, minus my initial distance, my equilibrium distance, over my equilibrium distance. So I could rewrite strain now. So I have now strain as a function of r. And r naught is just going to be a constant. What is our constant? It's always 2r, typically, for most metals. Our nearest neighbor distance, our equilibrium distance. So we can now go back into our derivation. So we said that we can relate, actually, or rewrite that here, this is our expression for our Young's modulus. So we can also rewrite our expression for force as well. So we could rewrite D, so we know that stress is equal to force per unit area, A squared. Again, if I assume that, we're in a cube, and there's, this distance is my equilibrium distance. Again, if we're simple cubic, this is true. But so if this cube distance is my equilibrium distance, I could just call this my r naught, and then so that's going to be my equilibrium distance. So if I'm pulling on this area here, it's going to be my r naught squared. So it's a little bit trickier when you look at cells that aren't that equilibrium distance. So you have to kind of make a little bit of an adjustment. But anyways, again, it kind of propagates. So I could rewrite my stress in terms of my force, and I could also take this derivative of my strain with respect to r. So if I take d strain dr, what do I get? Well, it's just going to be basically 1 over r naught. So hopefully people see that. So we'll use this relationship a little bit later, and actually we see it right here. Nice, clearly in our lecture notes. So going back to our expression, we said that E is equal to 1 over my atomic volume, and we could do this d squared u d epsilon squared. So I can kind of rewrite this expression. So I can go ahead and actually use some of these equations. So we said that my slope was d sigma dl, or excuse me, sigma d epsilon. So I'm going to use my old friend, the chain rule. So I want to write an expression where I have this in terms of r. So I'm going to do, and actually use it over here. So I'm going to do d sigma dr, and then dr, excuse me, dr de. And so those are going to cancel out, and it's going to leave me with my double derivative here, essentially. So I do that, and I can get my expression right here, 1 over r naught here, and then that's it. So I have this expression. I've rewritten it in terms of this, du d theta and all these other good, these good things. Excellent. Let's get on to the next expression. Thanks. See you in the next video. Actually, before we get into the our next derivation, let's take a little bit closer look and kind of go into this expression for those of you. So let's go ahead and take a peek. So we know that d sigma, excuse me, is equal to, oops, I don't need to do that. Let's go over here. Oops. Uh-oh. Looks as if my system doesn't really want to be in the tablet mode. But there we go, we're back. All right. It's equal to, as we kind of saw up here, df r naught squared. So df over r naught squared. So if we do d sigma dr, what we're going to end up with is as follows. So I'm going to equal d sigma dr, that's going to equal df dr, I'm just doing d or little d differential, it doesn't matter, 1 over r naught squared. What about dr de? Well, I know that de dr is 1 over r naught, so this is going to be r naught. So r naught. So what I'm left with is an expression that looks like this. E is equal to 1 over r naught, because r naught multiplies out here, so that cancels. So 1 over r naught, and then I have an expression like this, df dr. But I want to write it in terms of my potential energy. Remember, we know that the force is equal to minus the potential energy, minus the gradient, excuse me, of potential energy. So my force is equal to minus du dr. Now, you'll notice that this force is negative. So you might think we have to plug in the negatives here, but again, if we did that, we'd get basically a negative value of your Young's modulus. So if you think about it, again, we're looking in terms of kind of energy and curvature, and when is energy, or when is our material values positive or negative. So that is a kind of thermodynamic argument. So we're going to lose that negative, but we could relate that essentially to our potential energy, especially at our r naught. So we can go ahead and proceed with this. So if I plug that in, now I can see that my Young's modulus is equal to 1 over r naught, d squared u dr squared. Again, as long as we're evaluating this at our, at a strain of 0, essentially, effectively. So if we do that, then we are good to go. So we can move on to the next iteration of this and figure out how we can look at it from just looking at your elastic strain energy. Thanks. Bye. Sorry, one more hold your horses. So you may be asking again why I know that the force is equal to minus the gradient of a derivative. But think about it here. We are looking at, that's the force essentially between my atoms. So we're looking at what is the tensile force. So I'm going to apply a force like this, pulling those atoms apart. So the tensile force needed to stretch my bonds to make it go from this system to, basically over here, to this system where I'm stretching my bonds. My bond length is increasing. So the tensile force is going to be essentially minus the force between the two atoms, because it's opposite, right? They're pulling themselves back together, so the force is going to be minus that force. So really, the tensile force, you could even call it T, is going to be minus a negative potential. So with respect to R. So that's how you kind of get that positive one. So just so that, again, something food for thought in terms of how do we actually obtain and get that value. So hopefully that makes sense. Now, I promise now we'll get into the next one in the next video. Thanks. Bye.